Today is a good day to shoot monsters. So that's what we're gonna do. We're gonna shoot this guy. And I think I want some kind of effect when you shoot the monster with your laser. I'm gonna make him spin around in a circle, and that'll represent that we've hit the guy. So how do we spin him around in a circle? Well, as you've probably guessed by now, we're gonna use matrices. And as usual, we need to get 3 vectors that are going to be our basis vectors for our matrix. Okay, and as that should be a Z. And as we do things with these basis vectors, the matrix will get different properties. So what we're doing now is we're going to rotate our basis vectors. And then anytime you run a vector through that matrix, that vector will be, you guessed it, rotated. So the task of the hour is to rotate these basis vectors just like this and make a matrix out of those rotated basis vectors. So we're going to focus here on the X and Z vectors because, as you can see, Y points straight up. If you spin in a circle, up is up and it doesn't change. So it's just the X and Z vectors that need to go around in this circle. So let's break out our trigonometry triangle, okay? Because this is we're going to be depending a lot on this. And in fact, this might be a little bit of a review from when we did the Euler video. We did when we did the yaw. We did a calculation that was very similar to this, and this is my SOHCAHTOA mnemonic. If you haven't seen this before, don't worry about it, but the basic idea is that this guy right here, this is going to be our angle theta, and we're going to rotate our vectors by theta degrees, okay? And so this length, the length of this vector right here is 1, and so this is opposite over hypotenuse, this is our y. And y and sine are usually the same thing. This right here is our cosine theta, and this right here is our sine theta. So this actually gives us the components for our x vector, right? And just like when we did the Euler video, we're going to get an x prime vector. This is our rotated x basis vector. It's going to look like this. The x component is cosine theta, the y component is 0, and the z component is sine theta. Okay, now our y vector is going to be even simpler because, like I said before, we're not gonna change the y at all. When we spin around, up is still up, and our y vector continues to point up. The tricky one is the z vector, and it faces off like this somewhere in a 90-degree angle to our x vector. This is the x vector. This is the, I keep writing y when I mean z. This is the z vector. And here are our axes. That's c and that's x. That's the x-axis. That's the z-axis. You can see that our x vector and our z vector are at a 90-degree angle right here. And that means that where this was theta before, okay, this is also going to be theta right here. And that makes it super easy to figure out what the components of z should be. Ooh, doggy. So let's see. Our y component is going to be right here. Here's our y component. And we see that it's the same thing as this length right here, which is just the, if we go back to our mnemonic here, it is the adjacent over the hypotenuse. So it's going to be cosine x. Is that right? Adjacent over hypotenuse for the y. So I'm gonna do our z vector right here. We're gonna get something for x we don't know yet, and then 0 for y. And then z is going to be cosine theta. There we go. Now here is our, I'm going to switch to a color again. Here is our x vector, we can see it's going to be negative, and it's actually going to be the same as this guy up here. You see how these two are the same length? And that is the opposite. Everything is kind of weird since we're 90 degrees to the left, and I understand that. If this is confusing you, don't worry about it. We're almost through this section, but this is going to be negative theta. Okay? Oh, negative sine theta. Because sine is opposite over hypotenuse. There it is right there. And this is the opposite edge right here. This is a right angle. And you can see it's in the negative direction. It's to the left of the y-axis. So this guy right here is going to be negative sine theta. If this confuses you, go back to the Euler video where I did Euler angles. I explained it a little bit better over there. And that can serve as some review. So in any case, now we have three basis vectors. Let's make a matrix out of them. This is going to be a little bit weird because we have all these sines and cosines where we didn't before. But it actually lets us do something really powerful. So let's see, this is going to be, we're going to put our x basis vector down the left column. So that'll be cosine theta, 0, sine theta. And then our y vector is going to go down the middle column right here, 0, 1, 0. And then our z vector is going to be, there it is, negative sine theta, 0, cosine theta. Now we have a matrix that, depending on what the value of theta is, can rotate our vectors. So if theta is 90 degrees, then this matrix will rotate our vectors by 90 degrees. And if theta is 180 degrees, then this matrix will rotate our vectors by 180 degrees, and so on. And so we can just do a full circle. We can make our enemies spin in a full circle by just taking theta and starting it at 0 and then moving it all the way up to 360 degrees, and that'll spin the guy in a 360 degree circle. Great, let's go to the code section, and let's just do it. Now here I've already done a lot of trivial behind the scenes work that makes it so that when we shoot one of the monsters, this shot effect function gets called, and in this function we're responsible for doing whatever visual effect it is that we want to do to make it look like the monster got shot. So let's do it here. We're going to create our three basis vectors. Rotate x. So this is the x basis vector. And as per our formula on the right, we're going to use cosine first. I'm going to use this time variable as our theta, because the time variable, it will start at 0 and then it will increase. And as the time increases, it's like our theta will increase. And that means the angle that we're rotating will increase. So that's why we're using time as our theta. Then the y component is 0, and then the x component uses sine. So that's our x basis vector. Let's move on to the y basis vector. That's the easy one. It's just 0, 1, 0. And lastly, let's do the z basis vector. So what was it? Negative sine 0 cosine of theta. Now we have our three basis vectors. They're rotated in the way that we want to rotate them. So we'll make our rotation matrix. Back rotate x. We're going to pass in our three basis vectors rotated. Rotate z. And the last thing we should have to do is transform our rendering context, meaning that we're going to tell the thing that we're rendering right now, which is our monster, to be transformed by this matrix. All of the vertices, all of the vectors in that monster are going to go right through that matrix, which means they're going to be rotated when I shoot a monster. And there it goes. When I shoot the little guys, they rotate. When I shoot the big guy, he rotates. That's what we wanted. Awesome. So join us next time as we will continue to explore the amazing applications in math for game development. Peace.